this lesson, we continue our introduction to proofs by mathematical induction. Let's recall that a proof by mathematical induction is a method for proving that a given predicate is true for all natural numbers n greater than or equal to a fixed constant c. This method consists of two steps, the base case and the induction step. The induction step forms an infinitely long chain, and the base case tells you where to anchor the chain. It tells you where the chain begins. Let's give another example how this works. Let's consider the following predicate. This predicate says 3 raised to the n is less than or equal to n factorial. It's a natural question to ask. Is this ever true? And if so, which values of n make this a true proposition? Let's take a look at a table of values to explore this. Let's look at the first few values of n. When n is 0, 3 to the n is 3 to the 0 is 1, and n factorial is 0 factorial is 1. Yes, 3 to the 0 is less than or equal to 0 factorial. In fact, they're equal. Oh, but when n is 1, we have 3 to the n is 3 to the 1 is 3, and n factorial is 1 factorial is 1. So no, 3 to the n is not less than n factorial in this case, because 3 is not less than 1. And similarly, for n is 2 and 3, let's look at n is 3. 3 to the 3 is 27, 3 factorial is 6, and 27 is not less than or equal to 6. Maybe this predicate is never true for any n value. Let's keep scanning down the table. Oh, look! When n is 6, we're getting really close. So n factorial started out rather slowly, but now it's closing in on 3 to the n. And 3 to the 6 is 729, while 6 factorial is 720. It's still not greater than 3 to the n, but it's getting close, so that when we get to 7 factorial, indeed, n factorial now is greater than or equal to 3 to the n, because 7 factorial is 5040, whereas 3 to the 7 is only 2187. And if we check the values for 8 and 9, we see that 3 to the n is less than or equal to n factorial for all of these values n, where n is 7, 8, or 9. This column is less than or equal to this column. In fact, as n is getting bigger, this left-hand value is significantly less than the right-hand value. Now, 3 to the n is what is called an exponential function. Exponential functions can be found everywhere in nature, and they grow very fast as the exponent n increases. They're some of the fastest growing functions we ever deal with. But as we work our way down this table, we have found that somewhere near the value n is 7, that the factorial function catches up with the exponential function, and after n is 7, the factorial function overtakes the exponential function 3 to the n. This table illustrates how the factorial function grows even faster than the exponential function as n increases. From this table, we suspect the following claim. So from this table, we suspect that 3 to the n is less than or equal to n factorial for all n greater or equal to 7. And indeed, yes, this claim is true. Now, is it enough to check it for 7, 8, or 9? Well, no. But we can prove this claim is true using mathematical induction. So this is our base case, and then with our inductive step, we form a chain to prove that it is true for all values of n greater than or equal to 7. Let's show how to do this. So to prove our claim using mathematical induction, remember, we need 2 steps. We need the base case and the induction step. The base case is where the chain starts. From looking at our table, we're claiming that the chain starts at 7. And we observed that yes, 3 to the 7, which is 2,187, is indeed less than or equal to 7 factorial, which is 5,040. So yes, the predicate is true when n is 7, and so the base case is established. And the induction step looks like this. So we assume that the predicate is true for some value of m greater than or equal to 7, and our goal is to prove that the predicate is true for the next value, m plus 1. Now remember, it's perfectly valid and correct for me to assume that it is possible to get 3 to the m is less than or equal to m factorial for some value of m greater than or equal to 7. This has been established in the base case, so that in particular, when m equals 7, this is true. So there is a value m greater or equal to 7 for which this is true. Notice, I'm not assuming what I'm trying to prove. I'm not assuming that the predicate is true for all values of m greater than or equal to 7. So that is my ultimate goal, and so far I don't have it for all n greater than or equal to 7. I only have it for some value, namely at this moment I have it for m equals 7. And the goal of my induction step is to prove that if it's true for this value of m, then it must be true for m plus 1. And so how do we prove our goal? Well, we need to use what's given. So we need to be able to get from here to here. It's sometimes useful to look at it with numbers first, before we try to work it out with symbols. So let me give you a for instance. So we're focusing in on this induction step. We're assuming that 3 to the m is less than or equal to m factorial for some m bigger than or equal to 7, and our goal is to prove that the predicate is true for the next value, m plus 1. So how do we prove our goal? We start out with what we assume. We're assuming that this is true for some m bigger than or equal to 7. Now, how do I get from here to here? Well, I ask myself, how would it look if I had numbers? What if m were 7, for example? What could I do? Sometimes it's easier to see the algebra if I look at it with numbers first. So what would this induction hypothesis look like if m were an actual value, 7? We would have 3 to the 7 is less than or equal to 7 factorial, and our goal would be to get to the next step. We want to show that 3 to the 8 is less than or equal to 8 factorial. How could we do that? Now you can see why I'm inspired to multiply both sides of this inequality by the positive number 3, because that would get me from 3 to the 7th down to 3 to the 8th, which is part of my goal. At this step, I'm using one of the axioms of inequalities that says if we multiply both sides of an inequality by a positive number, then the direction of the inequality is preserved. Do be careful. If we multiply both sides of the inequality by a negative number, then the inequality gets reversed. Let me show you an example with numbers. So for example, here is a correct inequality. -5 is less than 9, and if I multiply both sides of this inequality by the positive number 3, then -5 times 3 is still less than 9 times 3, because -15 is less than 27. So it's still true. But if I were to multiply both sides of this inequality by -3, then you see that the direction of this inequality gets reversed, because 15 is greater than -27. And this order axiom always works this way. So if I have a correct inequality, if I multiply both sides of that inequality by a positive number, then the direction of the inequality remains unchanged. And that's the principle that I'm applying here at this step. Our base case says that 3 to the 7 is less than or equal to 7 factorial. We know this is true. This is a true inequality, and if we multiply this true inequality on both sides by a positive number, 3, the direction of the inequality remains the same. You might try punching this on your calculator and checking. It is true that 3 raised to the 8 is less than or equal to 7 factorial times 3. So this gives me part of the inequality I'm looking for, the 3 to the 8 part. How to get the 8 factorial on the right? Well, I wonder, is it true that this quantity might be less than? What happens if I replace the 3 with an 8? Does this work? And yes, it does, again, by that same principle. Because 3 is less than or equal to 8, that's a correct inequality. So multiplying both sides of this inequality by the same positive number, 7 factorial, and the direction of my inequality remains the same. So yes, 7 factorial times 3 is indeed less or equal to 7 factorial times 8. You might check that on your calculator. Make sure you believe me. Here, I'm just rewriting what I have written. So this line says 3 to the 8 is less than or equal to this quantity, which is less than or equal to this quantity, but 7 factorial times 8 is just 8 factorial. So you see the order axioms that I'm going to need to use when I do this proof in general. One of the order axioms is the fact that the inequality is maintained if I multiply both sides of it by a positive number. Another order axiom that I'm going to need to use is called transitivity, and that's the one that says if this number is less than that number, and then if this number is less than that number, then it follows that this number is less than that number. So that's the transitivity order axiom that I'm using to get to my final step. And I've proved that if 3 to the 7 is less than or equal to 7 factorial, then by correct application of my order axioms, it follows that 3 to the 8 must be less than or equal to 8 factorial. So if I do this with numbers, it gives me an idea what I need to do in order to accomplish this in symbols. Of course, this is not my induction step, because here I've only established that if it's true for 7, then it must be true for 8. I haven't yet established that the predicate is true for 9 or 10 or 11, so that's why I have to do it in general. I have to say, whenever m is greater than or equal to 7, if this is true, then this is true. So going back to the induction step, how do I accomplish this? I'm assuming that 3 to the m is less than or equal to m factorial for some value m greater than or equal to 7, and my goal is to prove that this is true for m plus 1. I can use this little calculation as a kind of a model as to how to proceed. What should I do next? What I did here. I multiplied both sides of my inequality by 3, and the inequality was maintained. So let me see, how does that look like if I do that here in my induction step? So if 3 to the m is less than or equal to m factorial, multiplying both sides of this inequality by the positive number 3, the inequality is maintained, and we have that 3 to the m times 3 is less than or equal to m factorial times 3. So that we have that 3 to the m plus 1 is less than or equal to m factorial times 3. Now what was the next step in my model here? What did I do next? I replaced the 3 with an 8. What's the corresponding value I should replace here? If I'm trying to bound m factorial times 3, well, my upper bound that I'm trying to achieve is m plus 1 factorial. So I need to multiply m factorial by m plus 1 to get m plus 1 factorial. In particular, that's what I did here. When m was 7, I multiplied by 7 plus 1, or 8, to get 8 factorial. And so in general, I need to bound this quantity by this quantity. Now the question is, can I do this? Is this true? Well, let's think about this in the same way as I explained this step down here. I asked the question, is 3 less than or equal to m plus 1? And if so, then multiplying both sides of that inequality by the same positive number, m factorial, the inequality will be maintained. Well, that's the question. I don't know what m is. Is 3 less than or equal to m plus 1? Oh, but wait a minute. We've made one more assumption in our induction step about the value of m. We've assumed that m is greater or equal to 7. If that's the case, then m plus 1 is even greater, isn't it? So if m is greater than or equal to 7, then m plus 1 is greater than or equal to 8, which is certainly greater than or equal to 3. And that's how I reason that this step is correct. I can write that down explicitly for you, like this, just to make sure I'm being perfectly clear. So again, how I accomplish this step is I use the fact that m is some number greater than or equal to 7. If m is greater than or equal to 7, then m plus 1 is greater than or equal to 8. This is another order axiom. If I have an inequality, I can add the same thing to both sides, and the inequality will be maintained. Here I added 1 to both sides. So if 7 is less than or equal to m, then 7 plus 1, which is 8, is less than or equal to m plus 1. And 8 is certainly greater than or equal to 3. And then the law of transitivity says if 3 is less than 8 and 8 is less than m plus 1, then it follows that 3 is less than m plus 1. And so that establishes that, indeed, if m is greater than or equal to 7, m plus 1 is certainly greater than or equal to 3. And then multiplying both sides of this correct inequality by the same positive number, m factorial, the direction of my inequality is maintained. And so if 3 is less than or equal to m plus 1, m factorial times 3 is less than or equal to m factorial times m plus 1. And that establishes this inequality here, which was my goal. You see in this induction step how I had to use everything that I assumed in my induction hypothesis. I had to use this fact, that 3 to the m is less than or equal to m factorial, and I had to use the fact that m is greater than or equal to 7 in order to accomplish this step. And now I'm almost there, because by transitivity we'll have that this is less than this, which is less than this, and consequently this is less than this, and that's our goal. And so, writing it down in detail, I've just rewritten this line. So 3 to the m plus 1 is still less than or equal to m factorial times 3, but m factorial times m plus 1 is the same as the factorial of the quantity m plus 1. So this is just rewriting this line, and then by transitivity, because this is less than that, and this is less than that, it follows that this is less than that, which is our goal, that 3 to the m plus 1 is less than or equal to the factorial of the quantity m plus 1, and so the goal is proved. And so we have proved our induction step. If 3 to the m is less than or equal to m factorial for some value of m greater than or equal to 7, then it must be true that the predicate is true at the next value, m plus 1. And so we have completed the induction step. We have shown that if 3 to the m is less than or equal to m factorial for some value of m greater or equal to 7, then it must follow that 3 to the m plus 1 is less than or equal to the factorial of m plus 1. And the conclusion is that the base case together with this induction step proves that 3 to the n is less than or equal to n factorial for all n greater than or equal to 7. And we've used the principle of mathematical induction to prove it, and it works like this. The base case says that 3 to the 7 is less than or equal to 7 factorial. So the base case says that the predicate is true when n equals 7. And the induction step says that if it's true for 7, it must be true for 7 plus 1, or 8. And then applying the induction step again. If it's true for 8, then it must be true for 8 plus 1, or 9. And so on. The induction step says that if it's true for 9, it must be true for 9 plus 1, or 10. And so on forever and ever and ever. So you can see why the base case together with this induction step establishes that this predicate is true for all n greater than or equal to 7. And this is just what we surmised from looking at the values in our table at the beginning of the video. So we've proved that this predicate is true for all n greater than or equal to 7, and not just for some n greater than or equal to 7. The n factorial function is indeed an extremely fast-growing function. It outpaces any exponential function. We had that n factorial is greater than 3 to the n. If we make this base larger, let's look at 5 to the n. Making the base larger will make this exponential function grow even faster. But no matter how fast our exponential function is, the n factorial function will be even faster than that. You could practice using mathematical induction to prove this last claim right here. That even if we replace the base of 3 with a 5 and make it grow even faster, the factorial function still wins.